to turn to our last speaker, Obadiah Bartholomy of SMUD, who's going to be talking about SMUD's new plan for decarbonizing their energy system. Let's see if I can, there's Obadiah.
Great, thanks Debbie, and thank you to you all. I'm not sure if any of you have been to can you see my screen? Okay.
Yes, I can see everything fine.
Yeah, not sure how many of you have been to an ESIG meeting before, but this is, these trainings seem like a little taste of it. By the end, you're like kind of overwhelmed with information. So anyway, I'm gonna pile on. Thanks to all the other speakers who went before me. So I'm gonna talk about our plan to get to zero carbon by 2030 and the role of DERs within that. Just to orient you real quickly, SMUD's about a 600,000 customer utility with a peak demand of about 3,000 megawatts. We're summer peaking, and we've got about 1,000 megawatts of gas plants at 5 different sites and are about 50% carbon free in terms of energy supply. So first off, I wanted to highlight a goal that was set forth by our board and later our CEO clarified. Starting last summer, our board adopted a climate emergency declaration, which committed us to, and the new CEO, to coming up with a plan within 6 months to get to zero carbon by 2030. I think they used the word net zero. Our CEO felt like we should just go all the way. So he said, we're gonna get to absolute zero by 2030. As I mentioned, we've got quite a significant gas fleet that we're going to be needing to look at in terms of retooling or retiring over the next 10 years. We have some experience with developing solar and wind projects, but this is really going to be a significant ramp up, over 3,000 megawatts of new renewable energy and storage development. We're going to be doing a lot of pilots, and I'll talk about a couple of those. And as well as some of the issues that we have with really trying to scale DERs and get them to be cost effective as part of this plan. And then the last component here was around the financial goals, and they set a goal of holding rates to no greater than inflation over this time. So I would say, you know, that this plan has plenty of ambition in it for us to work towards over the next 10 years. This is a quick picture of that trajectory of getting from 2 million tons per year, so gas plants operating at maybe 60% capacity factor on average, down to zero through a blend of proven clean technologies, natural gas repurposing, and then new technology and business models getting us there, that last 10%. We think DERs are really going to be crucial for you know, retiring certain gas plants, and as well for getting that last 10% of the way to the goal. And we've got kind of this near-term window where we've got a lot of learning to be done in order to get ourselves on this path and really make decisions in that 2025, 2026 timeframe to get us the rest of the way to 2030. This is a picture of those supply options that we've got, and you can see DERs there are fairly, have the potential to be fairly significant, between 360 and 1,300 megawatts of potential capacity from DERs by 2030. And I'll talk a little bit about some analysis we've done to look at that. But before I jump there, I'll start with some of the pilots that we're going to be doing to try and prove some of these concepts out. So we've got 2 virtual power plant pilots that we're launching this year and early next year. The first one of those is a multi-DER virtual power plant. You can maybe more commonly think of it as like a bring your own device power plant. We'll have about 30,000 customers by the end of the 3-year period. Most of those are going to be thermostat customers, but we're also recruiting EV and storage customers into that aggregation and asking the aggregator to provide us with some level of guarantee of the capacity for that. And then the second flavor is our storage-based virtual power plant. This is really coming out of our NEM successor tariff planning, where we've essentially moved from a full NEM 1.0. We're proposing to the board, hopefully for adoption in September, moving to an export rate that's set at the value of solar for us, which will be initially about a 40% reduction in the value for exported kilowatt hours. We're taking some of the fixed cost savings that result from that and piling those into an upfront storage rebate. And with that storage rebate, customers would be obligated to be on one of these two virtual power plants. So providing access to a portion of their battery, leaving them some for reliability, but providing access to a portion to be able to be dispatched by the utility either through direct control or through a critical peak pricing rate with automation. So as I mentioned, those two are launching pretty much right away, and we're hoping to get quite a number of learnings on bulk system dispatch and distribution dispatch and layered dispatch over the next 3 years as we integrate these into our DERMS system. So thinking about the value of virtual power plants in our 2030 plan, this is really something we had to dig into in order to understand whether we wanted to lean all the way in on virtual power plants and how far to lean, as well as to start to exercise some of the tools that are out there for evaluation and be able to refine our plans going forward. So we worked with E3 on this effort and actually leveraged 3 different models that they have. Their resolve, recap, and restore models, because they did not have a single model that had really done modeling of virtual power plants at this scale and with this level of detail. So we spent a few months with them working that out and had some pretty promising results come out of that. We found about 1,800 megawatts, I think it was, of VPP potential that could, in combination, displace about 500 megawatts of geothermal, pumped hydro, utility scale batteries, and wind energy. And it could do that with a potential total savings that was on the order of about 5% of our total spend over this time, both from a rate standpoint and from a revenue requirement standpoint. And that's not counting the fact that as we're investing in these VPPs, making payments for capacity, we're actually paying our customers. So as a customer-owned public utility, that's a real benefit for us if we can avoid paying developers for power plants and instead send that money back to participating customers. We felt that 5% was also pretty conservative because as part of this plan, we have a very ambitious electrification set of goals, reaching about 30% conversion of the transportation and building sectors to electricity by 2030. So really significant scale up from the, I think we're at maybe 2% today for electric vehicles. So really a big ramp up there that we've not fully accounted for all of the distribution impacts that's got the potential to create. We're doing ongoing work there to kind of validate distribution opportunity. But not all of that was stacked into this value. The VPP capacity was really dominated by electric vehicle, both V1G and V2G, about split in half in terms of capacity, and most of that being located at single family homes. We found there was really a significant amount of flexibility that these longer duration batteries will give EVs in terms of when they charge and discharge. And that flexibility really creates a potential to displace a broader set of resources. I think going in, my mindset was, at best we can displace some utility scale storage. And we really found, through this more comprehensive modeling that we were able to displace some of these other assets like geothermal and wind. And then the metering, another finding out of this was that the metering costs necessary to support ancillary services are currently out of the money for DERs, at least for the remote intelligence gateway costs that we looked at that are required for ISO participation. So that's something that we're going to continue to watch, how those costs for the metering evolve and what the rules are around aggregation to see whether that becomes something that we require or whether some of that, gets put into more of a automated response for certain services like frequency response.
Obadiah, you've got 5 minutes left.
Okay, thank you. I'll try and move it along. So this, sorry about that. This provides a spectrum around device control and value to the grid that we've been looking at for different programs ranging from behavioral demand response all the way up to a traditional power plant. The 2 VPPs I mentioned are kind of on the right-hand side of the spectrum here with either direct control or critical peak pricing that's coupled with automated technology response. We are also exploring behavioral demand response, and the idea there is that not all customers are going to have the money to invest in CPP-enabled technologies or may not want to give up the control, but may still be willing to give up something. And the premise or the question is, can we access some reliable value out of these low control approaches at a much lower cost than some of these high control approaches that we're considering on the right-hand side. In terms of accessing RA, currently our RA procurement process doesn't account for dispatchable DERs. Our load forecast includes customer dispatch DERs, not utility dispatch. Those are considered supply side, and as well it considers non-dispatchable DERs. And that, coupled with our planning reserve margin of 17.5%, defines our RA procurement need. Typically, RA procurement's around a 4-hour duration with no dispatch constraints, looking out over a 4-year horizon. Looking forward, this middle box is really where we hope to bring in dispatchable DERs into that process, identifying shorter duration and dispatch constrained need. We think we can meet about 300 megawatts of demand with these shorter duration dispatch constrained resources that still wouldn't qualify for RA, but provide a significant and similar capacity value to RA. And that if we can extend our procurement consideration window, that really enables these longer term VPPs to compete. So this is looking at longer term. Some of that resource adequacy value could be challenged. We see overlaps with utility storage. We see climate change and hotter summers, hotter extended heat waves, potentially impacting thermostat capacity value. As we move to a net load consideration with much more renewables, that's going to shift when we need capacity. And as well as we think about electrification, we're going to need to think about wintertime capacity and times where we may not have the kind of solar and storage we expect during the summer. All right, I'll delve into this. I'll probably maybe run out of time on some of the pricing considerations, but what we're looking at is moving from a world right now where we're providing pricing that provides a DER investment signal to one as we saturate our DERs, where pricing needs to shift to an operational optimization signal. And as we see really greater divergence of the bundled rate from our underlying costs, that's going to drive up our cost for recruiting DERs to provide grid services as customers have a higher opportunity cost to give up their retail rates and really access those VPPs. We also see a potential high strike price for traders that the retail interface creates, especially with critical peak pricing, where they're looking at both the cost of the resource plus the retail cost on top of that. Or the fixed cost component of that. So that really speaks to the need to address decoupling and fixed cost loss or cost shifts and equity issues in our business case, accounting for things like resource adequacy, which can bring in an additional $1 to $1.50 a kilowatt hour per dispatched kilowatt hour for peak focused resources. The only thing I'll mention on locational value considerations is really that we expect with the massive electrification of fleets and light duty cars that are coming, we're going to see a need for really standardized process around this. There's not a lot of value today. Maybe 5% of our capital spend is on DER addressable capacity. In the future, we think that's going to be a standard process that we need to account for that if we don't want to build up our distribution grid in a huge way. A plug for standardization. I think we're not going to have cost-effective aggregation if we don't get to standardization, and we also risk a significant amount of stranded assets and frustrated customers. So really need to, as much as possible, collectively push for standardization of communications protocols in particular. And the last thing I'll mention is that ESEG's DER working group has this US Open Networks effort where we're focused on making recommendations for DER integration to wholesale markets and operations through a report coming up in a couple months here. And as well, we are assessing the UK and Australian Open Networks efforts in an effort to recommend a US roadmap for a US version of open networks that looks across the electricity grid spectrum for how we can eliminate barriers to full integration of DERs. So thank you for the time, and I'll pass it back to you, Debbie.
Oh, thank you so much, Obadiah. SMUD's really very forward-looking in terms of how you're going to integrate and decarbonize beyond just the electricity sector. And it's really nice to sort of see a long-term approach to how to think about all of this. So I'm just looking to see, not seeing any questions, but I will ask, you mentioned the use, considering how maybe DERs might help with resource adequacy, and that you have currently a 17.5% planning reserve margin in your resource planning. So if we were to put in behind the meter battery storage, for example, and reduce load for you, would that mean that a megawatt of behind the meter batteries might reduce load so that you might obviate the need for 17.6% additional utility scale battery storage on the bulk power side because of that planning reserve margin?
I think that's right, Debbie. To the extent it's coming off of our load forecast or through an adjustment that comes in before our planning reserve margin is applied, then yes, that would reduce that additional 17.5%. On top of that, it also has a loss reduction value that we're refining through our ADMS and DERMS. So that's going to be an additional benefit that can offset some of the risk components that I mentioned around the resource adequacy that are going to feed into that risk adjustment to DERs in the RA process. Sure.
So that might tilt the scale a bit in terms of DERs then.
Absolutely, yeah.
Well, thank you so much, Obadiah. That was a great presentation.